Welcome to this lecture on first-order differential equations. Imagine you are driving a car on a long highway and your speedometer is broken, but you have a special gadget that tells you exactly how your speed is changing based on where you are and what time it is. A differential equation is exactly like that gadget. It is a mathematical puzzle that gives you the rate of change of something, and your goal is to work backward to find the original quantity. Let us dive in and see how this works. Now that we understand the basic idea, let us look at the formal mathematical definition. Why does this concept matter? Because in the real world, we rarely know the exact amount of something at all times, but we often know how fast it is changing. A first-order differential equation is an equation that relates an unknown function, typically called y, to its very first derivative. The order of any differential equation is simply the highest derivative that appears in it. Since this is first order, you will only ever see the first derivative and never a second derivative like y double prime. The solution to this equation is not a single number, but rather an entire function or a family of functions that makes the equation true. Building on that definition, we need to understand the different forms our answers can take. When we solve these equations, we categorize the solutions into three main types. First, we have general solutions. Because we are working backward from a rate of change, there are infinitely many parallel curves that could have the same slope. So, general solutions always include an unknown constant. Second, we have particular solutions. This is where we are given specific starting conditions, allowing us to pin down that exact constant and find a single specific curve. Finally, there are singular solutions, which are special cases that simply cannot be found from the general solution formula. We will focus mostly on the first two. Now that we know what solutions look like, let us learn our first method for finding them. This formula comes from a technique called separation of variables. Conceptually, if the rate of change can be written as a product of two separate expressions, we can physically separate them. We move all the y terms to the left side and all the x terms to the right side. It is like sorting apples into one basket and oranges into another. Once separated, we apply an integral to both sides to work backward from the rate of change. In this formula, x is the independent variable, like time, and y is the dependent variable, like position. If x increases, the area under the curve f of x grows, which directly dictates how the function y must evolve. Before we move on, let us see this formula in action with a concrete example. We are asked to find the general solution to the differential equation dy by dx equals 2x. We are given the rate of change and we need to find the original function. Because we are not given any starting conditions, we know our answer will be a general solution with an unknown constant. We choose the separation of variables method because the x and y terms can be easily isolated. First, we multiply both sides by the differential dx. Now, the left side only has y information and the right side only has x information. Next, we place an integral sign on both sides to transition from talking about rates of change to actual amounts. Continuing from our setup, we now evaluate the integrals. The integral of 1 with respect to y is simply y. The integral of 2x with respect to x is x squared. We must also add the constant of integration c to represent the general solution. This final answer represents a family of parabolas. Physically, this means that no matter what value c takes, the shape of the curve is identical, just shifted vertically. Because we were not given a specific starting point, we leave the answer in this general form, which perfectly solves our initial puzzle. This brings us to a visual representation of what we just calculated. What you're looking at is called a slope field. The horizontal axis is x and the vertical axis is y. Notice the grid of tiny lines covering the background. These show the required slope at every single point, dictated by the differential equation. The solid colored curves are the actual solutions, like the parabolas we just found. You can see how they flow perfectly along the path dictated by the tiny lines, much like water flowing down a rocky stream. Each different curve represents a different starting condition, showing exactly why that constant of integration is so important. Now that we have seen a general solution, let us tackle an initial value problem to find a particular solution. We are given the equation dy by dx equals negative 3y, along with a starting condition that y equals 5 when x equals 0. This equation states that the rate of change of y is proportional to y itself, which is the classic model for exponential decay, like a cooling cup of coffee. We use separation of variables again. We divide both sides by y and multiply by dx to group the variables. Then, we apply the integral to both sides to prepare for finding the original function. Continuing with our integration, the left side becomes the natural logarithm of the absolute value of y. The right side becomes negative 3x plus our integration constant c. To solve for y, we must remove the natural logarithm. We do this by making both sides the exponent of the mathematical constant e. The exponential function and the natural logarithm cancel each other out. Using the rules of exponents, we can replace the constant term e raised to c with a new simpler constant called a. This gives us our general solution for the decay process. But we are not done yet. To finish the problem, we use our initial condition. We substitute 5 for y and 0 for x into our general solution. This represents the exact moment the process started. Any non-zero number raised to the power of 0 is exactly 1, which leaves us with a equals 5. We have successfully found the exact value of our unknown constant. Substituting this back in gives our final particular solution. Physically, this tells us exactly how the quantity decays over time, starting from an initial amount of 5. Unlike our first example, this equation contains no unknown constants because our starting condition locked it down. So we have proven that we can solve these equations. This brings us to why they are so crucial. First-order differential equations are the absolute foundation of mathematical modeling in the real world. Without them, we could not predict how populations of animals grow or how diseases spread through a city. In finance, they are used to calculate continuously compounded interest, helping investors understand how money grows over time. In physics, they describe the motion of objects falling through the air with resistance, like a skydiver opening a parachute. Anytime the current amount of something directly affects how fast it is changing, this is the tool you must use. We have covered a lot of ground today. So let us review the most important ideas. First, remember that a first-order differential equation is simply a mathematical relationship between an unknown function and its first rate of change. Second, by using techniques like separation of variables, we can work backward from this rate of change to discover the original function. Finally, always remember the difference between a general solution, which contains an unknown constant, and a particular solution, which uses starting conditions to find an exact curve. You now have the ultimate tool for predicting the future based on current trends. Great job!